In this demonstration, we are going to compare a feedback loop to a feedforward loop to a dynamic feedforward loop. Feedforward loop with dynamic compensation. So here we have a simulator. We've got a heat exchanger. We've got product flowing in through the heat exchanger. We have steam flowing into the heat exchanger. The steam is heating up this product, and we are getting feedback here from this temperature transmitter. Our controlled variable is the temperature of the product out. Getting feedback here. This is our manipulated variable. We're manipulating the steam flow. And you can also see we're measuring the flow of the product through, and we are compensating, we're using feedforward compensation by measuring the upstream flow. And when we have a change or flow disturbance here, our valve will automatically move to try to prevent an overshoot in our controlled variable. So first off, I've got our controller in automatic. Click on the faceplate here. You can see it's in auto and with a set point of 50%. What I'm going to do first is I'm going to bump the flow rate here down to 40 liters per minute. You can see here on our trend we have a signal on the y-axis and time on the x-axis. The total time here is 1 minute. We're trending in red here, we're trending the process variable or the controlled variable, which is the temperature of the product out. We're trending it the red pen. With the green pen, we're trending the disturbance, the flow rate here. So when I adjust that, we should see this line spike. The black line up here is our controller output, the signal to our valve. So by looking at, those are the three things we would like to watch, and it's going to really help us demonstrate feedback versus feedforward versus dynamic feedforward. So I'm going to close the controller faceplate here, and I'm going to bump this to 40 liters per minute. So you can see it spiked down, and you can see our process here, our temperature started to rise up, and then the feedback caught it and started bringing it back to the set point, 50 degrees C. So you can see right here I have this button for enabling feedforward. It currently is not enabled, so we are only controlling with this feedback loop here. We weren't using the feedforward. And so we had a decent overshoot, almost 10 degrees C. If this was what was our transmitters calibrated for 0 to 100 degrees C, 0 to 100. So it rose about at a 10 degree C overshoot. So now what I will do is I will go and enable feedforward. I've already done our calculations to figure out the feedforward gain. I bumped the disturbance, watched the process variable, bumped the controller output with the control loop and manual, and watched the process variable, and came up with these calculations here. Figured out the gain related to our manipulated variable to controller output, Kp, gain of our process, and Ku, standing for representing our disturbance, change in our disturbance, change in the process variable. Made a 10% change in both of these, positive 10% change in the disturbance and in the controller output signal. We saw a 10% change here and a minus 5% change here. Give us these two values. And then to figure out our feedforward gain, we used the gain of the disturbance over the gain of the process. And that is going to be a negative value. Negative, negative, and a negative cancel out to be a positive. We have 0.05 for our feedforward gain. So that 0.05 is entered in here. So I've got it enabled. Now let's see what this does. So I'm going to go ahead and change the disturbance again back to 70. And let's watch our process variable, the red pen. You can see the overshoot is very minimal. So feedforward gets rid of that overshoot that feedback cannot get rid of. especially in slow processes like this where we're trying to control a temperature. Okay, so what's the point of dynamic feedforward compensation now? Well, up here in the top left corner, I have time constant, 2 time constants, and 2 dead time values that I can change, and that is going to change the time constant for our temperature valve, how it reacts with the controlled variable, and the time constant for FT201, which is where we're measuring a disturbance. I can change the time constant and dead time in relation to the controlled variable here as well. So these both could have differing time constants and how they affect our controlled variable and differing dead times. So I'm going to go ahead and adjust those, and then we'll see how that affects our feed forward control. Okay, so now the temperature, the TB201, the temperature control valve, its time constant of 5 seconds. So that means it's going to take 5 seconds for it to get to 63% of its total change when the valve opens or closes, or sorry, opens a little bit more or closes a little bit more. It's going to take 5 seconds for it to get to 63% of its total change in temperature here on the controlled variable when that valve moves. Down here, 2 seconds for a time constant and a dead time of 10 seconds. That means after we make a change here, it'll take 10 seconds before it's seen over here. So time constant relates to 63% of the total change, and the dead time is how much time until the process variable or the controlled variable over here actually starts to change. So they differ. Let's see what this does now. When we have, right now we have our dynamic feed forward compensation turned off. We're going to be using this to compensate for those differing time constants and differing dead times. So let's go ahead and bump the process back down to 40. You'll watch and see our valve move right away when we have this disturbance. And you can see we have quite a bit bigger overshoot now. And then we even had an undershoot or overshoot here, and then another overshoot here. And that is because of that differing dead time. So we need to compensate for this. So to do that, to figure this out, we need to take the dead time of the disturbance and subtract the dead time of our manipulated variable, the valve, up here from it. So we'd have 10 minus 1. So we'd have a dead time of 9 for our dynamic compensation. Our lag time is going to be equal to the time constant for the disturbance or the flow transmitter. So it'll be 2. And the time constant for temperature valve 201 is going to be our lead time, 5 seconds. There, so now we have our dynamic feed forward lead time, lag time, and dead time compensation entered in. Now we're going to go and step the loop again back up to 70 liters per minute. Sorry, the disturbance back up to 70 liters per minute, and see how that affects our red pen here, the temperature. So you can see our disturbance jumped up. We'll wait a few seconds at least, minimum of 10 seconds to see what happens. You can see there our valve spiked up, it waited the 9 seconds, and now you can see how it's adjusting and it's compensating for these 2 time constants, and you can see the blip in our controlled variable is very minimal. So the temperature had a very small blip, versus before when we were not using dynamic feed-forward compensation, it was quite large. So dynamic feed-forward compensation is going to do the best job of removing controller overshoots.